Thank you.
So we are here to show why actually we claim that Scala can be the next distributed data science language. So this talk will be given by myself and Petrella over here, the monkey, with Dean Wampler over here from Leidband, if you want to present yourself.
Also the Hunger Games, apparently.
President Snow, buddy. I mean, he's there just for you.
Yeah, the Leidband is only the day job, actually. Yeah.
Right. So distributed data science. Why distributed data science today is actually the new interpretation of big data. What I meant by that is that big data, until recently, was considered to be only distributed computing at some point in time. And only distributed computing doesn't explain why big data is now pretty hot. And this is also something that I want to explain today, why big data became hot at some point, and what are the different key that we need to have in mind. So, now, when I say that distributed computing is pretty interesting with big data, it doesn't explain why it's very important now. However, distributed computing is very old in some point in time because it was used in academy for, I mean, maybe 30 years, right? So why now it's pretty hot? I would like you to think about that for 30 seconds, for instance. So why distributed computing became at some point big data? It existed, and it became big data. Why? Why this transition happened in the IT world? Just give it a thought for 15 seconds now, if you like. How this transition happened. So big data is actually because we're computing. It's important, right? So the thing is that business. It's all about business, okay? So if we think about big data, we think Google, right? But what Google wanted to do initially, they wanted to do business with ads, okay? And in order to achieve that, they had to, be very good in performances, accuracy, and so on with data science. In order to be very accurate, they had to harvest the whole information accessible for free, which is the web at that time. So they wanted to aggregate everything, to compute things on that, and then finally discover information in there that they can use in order to make money out of it. Okay, so they had to process the whole data. But why didn't they use HPC then, high-performance computer, to do that? Why did they invented stuff in order to achieve these performances? Actually, they didn't really invent it. These different theories like MapReduce and Google File System. I mean that they didn't really invent it because actually what they did is that they harmonized the way scientists were working with HPC. When you worked with HPC, that means that you had the big data file, then you had to split it manually, then you had to launch processing on your cluster of CPU and GPUs, and then aggregate them manually with bash script and so on and so forth, right? So you had to do that as a scientist at that time. So what they wanted to do is to harmonize the way you want to work with your distributed cluster, okay? And why they were so popular is because now it was simple to do it, okay? So with this harmonization, it was simple. But not only simple, it was also resilient. So this is what they added to the system, the resiliency. Because, bash scripts are not really resilient. So they had this resiliency to the system with Google F system and with MapReduce. And they had to introduce that for business again, because they had to be productive. They don't want to have scientists restarting the full job when it failed, or having scientists conflicting their jobs on the cluster. So they wanted to be very efficient on that. So that's why they also thought about that. So this is mainly about business. So distributed computing became big data because of business. But nothing really changed unless the harmonization that brought by Google. So then Hadoop. Okay, Hadoop is what? for me, it's an enterprise-ready open source implementation of these first papers, right? So there are other papers from Google that were very interesting to check, like Petrella or different others. However, about Hadoop itself, it's pretty interesting because it's an open source implementation, but it's based on the JVM. And JVM is crucial here. Why? Because it became something that can be deployed directly in an enterprise platform. So you can go to a department and install Hadoop because it's based on the JVM, and the system ops and so on were pretty used to deploy JVM things. If you go to a defense department, they have JVM running all over the places, so they can integrate Hadoop easily. And then you can start computing stuff on your whole data set. However, Hadoop, you know that, has a pretty tough model. Implementation are pretty hard, so the interfaces are clunky. And also, something very important is that the time for the first result is very long, right? The installation is not easy, especially in a single machine. Yeah, so if you want to write a simple word count, you have to build the package and so on and so forth, right? So this is why the ROI for the business wasn't clear, and the programmers didn't invest a lot of time in there. I mean, the mainstream developers, like, majority of the developers, because of these points. However, Spark came into the party, and a lot of people was claiming, yeah, you know, Spark is 100 times faster than Hadoop. And I say, who cares, right? I mean, regarding the importance of Spark in the ecosystem, this is not this factor that was very important for us. Actually, what was really interesting with Spark is that they added a new level of simplicity on top of Hadoop, for instance, or distributed computing framework. That means that now, in order to have the first result with Spark, it takes a few minutes, while with Hadoop, it took a lot of time. So Spark gained in popularity because you can install it very easily, so it's just a tar. You can run the REPL in order to do quick experimentations, and a word count is like 2 lines, okay? So that means that the access to the first result is very, very fast. And also, the APIs that you use are very simple, and they are very looking like the APIs that you are used to use when you do Python, R, Ruby, or JavaScript, and even Java 8 now. You know, this kind of chaining functions, high order functions. So the one of that factor is important, but this is not why Spark get this popularity. Well, okay, so now let's say that Spark added this simplicity into the party for big data computing. That means that some engineers most probably got bored because they thought, or they think still, that now it's easy to do distributed computing thanks to Spark. So they say, okay, so now I can do distributed computing, so what can I do next? Well, they look around and they say, okay, so we can do data science now. So I want to become a data scientist. Well, which is not always the good move, of course, but anyway. The thing is that they are now getting back to where Google started. Okay, so Google started these different theories in order to do data science, and now after maybe 10 years, we got back to this point, and we say, no, yeah, so now we want to move forward. I don't mean that at the time of Hadoop we didn't do any data science. Of course, Matlab was there, very good, very performant. However, it suffered the same problem as Hadoop. The interface were clunky, the implementation was hard, and the setup was also pretty tough. So the thing is that now the IT guys are turning back to the business and say, okay, so what do you want to do now that we can compute stuff easily and resiliently? The sad thing is that they quickly made wrong choices because business is decoupled from IT generally. And this is something that we will cover after what Dean will cover now about why Scala is a good language now. Okay.
So actually, you can get the stuff I'm about to demo at this GitHub link. Data Fellows is Andy's company, Scala for Data Science. And there's also a link to the slides there. So I'm actually using something called the Spark Notebook that Andy started. It's, if you've ever worked with a notebook environment like IPython, Mathematica, a lot of the data science tools that build these notebooks that are sort of a computer version of the old lab notebooks where you can put in formulas, draw graphs, put in notes, and so forth. I think this is a great way to work with the REPL, actually. And it's if you've ever used like the worksheets in Scala IDE or IntelliJ, it's kind of similar. You can go back and edit code, rerun it. You can embed, like I said, commentary. You can do graphs of results, which unfortunately I don't have an example of that, but that's another nice thing. If you have data and you want to see what it looks like, you can go ahead and graph it. But what I want to do actually is walk through some bullet points of the things about Scala that make it great for doing data science. I won't cover all of them. There's actually like a secondary list that I won't cover for time. Some of the things in that list are actually really valuable for general Scala use, but actually less important in Spark use. Like, for example, recursion and the tail call optimization in Scala. Actually completely useless when you're writing Spark code. You don't need it, but it's obviously very nice for regular regular Scala code. So anyway, these cells that I'm evaluating by hitting shift return are basically markdown. So this is my commentary. And as far as Spark goes, it supports Python, R, Java, and Scala. And most of the data scientists come from like a statistics background or whatever, and so they tend to use Python and R. But there's actually some nice advantages of using Scala instead. One of the first advantages is the nice balance between object-oriented and functional programming. So I'm preaching to the choir here, but all the benefits of functional programming are here, like immutable values, no side effects and all that stuff. I won't even read this list because you all know this list. But you might take this list and take it back to your colleagues who are insisting they should do Java with Spark, which I think is the stupidest idea ever. Well, maybe not the ever, but it doesn't make any sense. But on the other hand, we use objects for encapsulation, modularity, and all that stuff. So it's a nice. We can all argue about the balance. I mean, this is one of the things our community loves to do is argue about whether Scala is pure enough and all that stuff. But pragmatically, it works really well. I also have cells in here where I compare. All right, what about Python? It does have some functional features, maybe not as well thought out. R is more of a math language, so it doesn't really have the same concepts and so forth. And Java, except for the fact they finally added lambdas, which was a huge step forward, there's a whole bunch of stuff still missing that we'll talk about as we go on here. So actually, let's look at some examples to see how concise things can be. So I'm going to write a helper function to compute if a number is prime. I stole this from Wikipedia. It's not even a very good function, but it's just here as a helper. This is actually the first code, so when I hit return here, it's going to compile that code. This green bar is here because we've been running Spark jobs. It's like a status thing at the moment. It's just blocking the output, but not being very helpful. But all I did was define a function, is prime. Now I can use that. So now I've got some more commentary, markdown. Here I'm commenting on the virtues of the previous function as far as like no side effects and all that sort of stuff. But we can also write regular Scala code. So here, just as an example, I'm going to find all the primes between 1 and 100 and group them over whether they're prime or not, and then print out the results. Print out the number of primes versus non-primes. And it turns out, curiously enough, there's actually almost exactly 3 to 1 of non-primes to primes. So not a terribly exciting result. Slightly interesting, just how close it is to being exactly 3 to 1, but nevertheless. Code that hopefully this is very recognizable to all of you. The thing is, in a minute, I'm going to take the 3 lines that end this expression and do them on the Spark side without any modifications. And this is one of the great things that the Spark program recognized is that this collection API is actually really powerful for data. So why don't we just use it and maybe adapt it in ways that we have to, like it's lazy versus eager and things like that. But here's a Spark program that basically does the same thing. I'm going to take a range, I'm going to parallelize it, which means turn it into Spark's internal data structure called a resilient distributed data set. And then the next 3 lines are exactly what we just had to do this calculation. because it's a lazy collection, I have to force it to return the results. And that's what this collect method does. It actually copies it from the RDD back to a Java, or rather Scala collection, and that will materialize it. But otherwise, it won't. There's a little bit of output here, but there's the result. Same thing that we expected to get. Notice it comes back as an array. So we can take what we know about functional programming, or Scala in particular, and actually use it straight away. There's a bunch of extensions they've added. There's ways in which they've taken that API and made it work in Python and R and Java, so it's a little alien to those language communities, but it feels right at home for us. Another important benefit over Java in particular, less so for the other languages, is the fact that we have an interpreter that we can work with and that I'm using right here under the hood. This is obviously not news for us, but for people from the Java world, this is so valuable that I can do stuff interactively like this, whether I'm using a notebook or something else. Use tuples all the time. This is one of those little minor things that we kind of take for granted, but a lot of code looks like this when you're working with RDDs at the bottom here. Let me scroll this up a bit, where you're going to treat tuples as like your record type. And it's just very convenient to be able to manipulate the elements in the tuple to do pattern matching, which I'll come to in a second, is another advantage. So this becomes really useful. Python has something similar, but not quite as nice, and Java, of course, doesn't have it at all. So you end up writing crap like this, which is this thing that Spark had to add because Java doesn't have any sort of tuple type, so they made up their own immutable pair type. 2-element tuples, key values, are the most common tuples you'll use, and this is how you would do it in the Spark Java API, which is just noise. But of course, pattern matching is something else that's sort of dual to tuples in the sense that it's, I can put stuff in records, now I need to rip it apart, and there's no better way to do it than doing pattern matching. So here it's the same program, but now I'm using like useful names for the fields. I'm throwing away things I don't care about, all just by using pattern matching. And then I describe what's going on. So there's a lot of details in the notebook here that are familiar to us, but maybe less familiar to people coming from other languages. And then the fact that we can do pattern matching at arbitrarily deep levels. Here I just did an assignment where I ripped apart a nested tuple into its constituents. Case classes are an interesting beast. They also are really good for representing records as well, when you want a name and not just a position, like you would have with a tuple. What's interesting about case classes, though, is that we're moving in Spark towards very, very optimized in-memory representations of data, which I'll show you an example of in a second. And in a way, you really don't want to instantiate a case class for every record if you have 1 billion of them or something. But it is a great way to think about the schema and only sort of move away from something that's a little bit more record-oriented, not like data structure-oriented later on for performance. But for right now, it's a great way to think about like a person type or something. And Spark integrates very nicely with this to let you use these as record types. I describe what the case keyword does. That's obviously something you guys know. But here I'm sort of synthesized an example where I created 2 person objects with made-up ages for Andy and myself. Maybe you're 29, I don't know, I'm definitely not 39. And then just once again doing pattern matching on it to tease it apart and then actually putting out tuples again, just as an example of how you can manipulate the data very easily to convert it to the format you want. Type inference, this makes, we all know this, but boy, there's nothing like having the types when you want them, but having them disappear in the background when you don't. So you can infer types, obviously this is a trivial example of inferring integers. But even things like just having it tell you what it inferred, so you don't have to know exactly what this particular method returns, but just by seeing what it returns, now I know that, oh, I just got a RDD and it came out with this data structure for the records. So we just don't have to put in a lot of the usual type annotations we have with Java, but we get these really useful messages about what we just did, which is fantastic when you're learning this API. Whenever I've used the Python Spark API, I inevitably find myself printing the first few records so I know what I ended up with, because I'm not sure, there's no information from Python that tells me what I just created. So I really like that balance of type safety as well as expressiveness. A couple last points, and then I'll switch back over to Andy. As we all know, it's a great tool for building domain-specific languages, and a specific example in Spark is the way they have supported the notion of doing SQL-like queries. This is so you could call it an API on top of the core called the Data Frames API, and it's managed by this thing called a SQL context. So here I'm just doing some imports and setting up some stuff that I need. But, and also I'm going to load some data here. Let me see, this is all set up. So we've got this environment variable that we defined when I started this thing. And yeah, what am I doing here? I'm getting the current path. Actually, it turns out I don't need that line anymore. But here's some data that's like, it turns out you can download a data set for all of the public airline flights, commercial aviation for the last 15 or 20 years. It's rather interesting to play with if you fly a lot like I do, but this particular one is a JSON file that has data about all the airports in the country. And there's this convenient API here where I'm using the SQL context to just read JSON. It parses it, it infers the schema. You can see that it's printing the schema below here as a result, so that's really nice. It does this with other file formats like Parquet as well. Those of you who've worked in Hadoop know what Parquet is. Caching tells Spark, keep this in memory because I'm going to keep reusing this data. And then there's this nice show routine that prints out something that looks like, if you've ever used a database, interpreter, you get this sort of table format when you look at the first, in this case, 20 records. So here's the first 20 airports that showed up in that list. But now we can write SQL-like queries. You can either embed a SQL query in a string, which, as we all know, is bad because it's stringly typed, right? At least that's what we were told in computer science school or whatever. Or we can do this sort of DSL. And that's kind of the point of this section, is that we can write expressive DSLs pretty nicely that encapsulate our domain knowledge. And this is very close to a Python DSL that was the inspiration of this API. But here I'm just doing a group by over the state and country for these airports, and then basically ordering by descending count how many airports are in each state, basically. And it turns out Alaska has most of them, I think, because it has lots of little tiny airports. Actually, did it sort correctly? Let's see. Oh, I scrolled up too far. But yeah, didn't actually run that one yet. Here we go. So it showed me the schema. That's this print schema thing. And here it is. So Alaska has quite a lot of little airports scattered out in the backcountry, and Texas has a lot, California, and so forth. So we can do SQL queries. And what am I doing here? I just reran it again, I guess. All right, and there's some comments about Python and so forth. All right, I'm going to skip the rest of these. Like I said, there's some things that we really love about Scala that are not as important in Spark, but are generally useful, like recursion. You don't really use it much in Spark, but a lot of these other little features like no semicolon string interpolation are things that we all know and love that just make our lives a lot better. So with that, I'll go back into presentation mode here and let Andy finish up.
Cool. So yeah, this notebook is awesome because, I mean, we can take it, go to the data scientist and show all the great stuff that they can use with Scala. And actually, if you look at it, it's not so far from Python. There is no lambda everywhere. That's the good part of it, I would say. Yeah, this is lambda hell, right? In JavaScript, you have the callback hell. In Python, you have the lambda hell. So yeah, I recommend everybody to go to this GitHub repository to check it out, to test it, and to make recommendation, PR, whatever. I mean, this is a good tool for us to demonstrate that Scala is actually a good language to go forward with data science, and especially with distributed data science. So, well, the Scala is the distributed data science, so if we want to be very harsh. Well, so data science is actually what brings real added value for the data, right? That means that we can now create models that can work with distributed data, and so we can run algorithms on whatever size of data we have, or speed, or variability. You know, this I don't know how many V's we are now, and the fact is actually data science is not new. Distributed computing wasn't new, and data science neither, right? Actually, data science is something which is used for ages, And there are even businesses that are completely relying on data science to be profitable. If you think about insurance, what is insurance? They don't have hardware, they don't have software, they just have your data, and they make money out of it. Okay, this is the only thing that they have. They don't even take your money to deal with it. They just need your money and maybe help you when you have a problem. So based on your data, they can make money because you're scared about the future, right? So in order to do that, they have to analyze your data efficiently, accurately, otherwise they might screw themselves, right? So the data science is not new. So what's the difference now between big data of yesterday and today? There is one thing that I think is that actually now the ownership of big data, being data science now, is moving from IT teams or IT hands to data science teams. Okay, so this is what happens now. This is pretty sad, I would say. And the thing is, since this ownership is moving, and with these tools, this distributed computing framework, distributing clusters, and so on, the data scientists are feeling a little bit scary as well. So they put themselves in the defensive position, saying, yeah, actually we were running this insurance company for years, so we don't really need this stuff. Okay, so we were already accurate, right? So otherwise, how could we be profitable since then? So they put themselves in the defensive. So what they do is generally they say, okay, so now I want to have proofs of evidence that learning these technologies and systems are worth, right? It's worth, yeah. So that means that they enter this exploration phase, and they will hit two barriers mainly. The first barrier will be the tool chain, okay? The tool chain is involving a lot of different things like Cassandra, Spark, HDFS, Parquet, we just heard about it, and also creating programs that you deploy somewhere, that you ask a scheduler to run and things like this, and then you go to the console in 7 machines in order to see what's going around, and then you have serialization problems and so on and so forth, right? So this is the toolchain that they have in their hands now. So this is upsetting for them, where they can just start a Python console, create a sample of the data, I don't know how, and then run a model that they can import a package from R or Python. So this is the first barrier that they hit. The second barrier, so of course now if you go to Python or whatever, so they have point and click UIs or drag and drop with boxes with code in it or whatever, and this is what they like. The second barrier is the language. So Python, R, these are the language that they are used to use, and they want to keep their habits. So when we say, okay, so maybe it's not the right way to go, Spark, for instance, is implemented in Scala, and maybe it's a good move to use Scala either. The problem is that if those barriers are influencing the toolkit that you want to use in your team, then you will hit a productivity problem. So they say that if they have to use Scala, they won't be productive. What I say is that if they don't use Scala, the whole team won't be productive. Okay? So why do I say that? So maybe I need to define now what is a team then. If you think about Spark, Hadoop, Cassandra, Kafka, and so on and so forth, how those frameworks or tools are actually implemented on the JVM, okay? And the thing is that if you ask the data scientists to work on these things, they will say that they have a productivity problem, right? So the productivity will drop down because they won't have the right libraries to use them. So and if they have to use JVM, they will say two other things. They will say, yeah, but my models aren't implemented in Java or Scala, so I cannot use, I don't know, easily a random forest, or random forest is like the silver bullet for them, for most of them, which is most of the time wrong anyway. And also, again, the tooling are not very I cannot work smoothly with the current tooling. I don't want to use IntelliJ. I don't want to use Eclipse, right? I want to use a notebook, for instance, right? So like the one that you just seen. So the thing is that, again, so if we introduce these different concepts into our team, then we will hit a productivity problem. So what is a team? A team is a mix of data scientists and engineers. So if you remember, like maybe 3 or 4 years ago, so we integrated the sysops into the IT engineers team, right? Because it makes sense to have those guys working all together into the same direction. So actually what I would say is that data scientists have to be part of the same team. Why? Because at that time they have only one goal, is that to create one data product all together. Otherwise they might, go in one direction, each of them, and then you have to always, solve fights internally and things like this. So what I said that actually a data scientist nowadays, his work is to produce 2 things. A job that has to run in a distributed computing framework because it uses distributed data, so this is one thing. And the other thing that he has to produce is a service that has to be consumed by multi applications. So just returning a PDF with a few plots and a few tables is not is not worth anymore. I mean, it doesn't help anymore because the data is moving too fast. The information evolves as well too fast. It changes, so we need to be agile and reactive with the way we are dealing with the data. So that means that we need to deploy services that can that are enabling predictive function, but also that are giving an interface, a view layer onto the data, which were the sources, the output, and the intermediate steps. So this is what they have to produce. That means that they should be able to write spray code. I mean, they come from Python and R, and they have to write spray code. Even us, I mean, say that sometimes it's a bit hard to write those code. I mean, that's why they need to be, in very close relationship with somebody that can write this kind of code and that can deploy this job into production. Otherwise, they will just fight. Sorry. So. Well, yeah, actually, so the team it has to be, everybody working on the same thing. Otherwise, if we have people working on Python one side, let's say, so I have this script. It produces this feature tables. It's pretty neat, and then I can predict that onto that. So it's a pretty good script. It's Python script. So now please deploy it. So the guys will say, yeah, but I don't know how to deploy that. I don't even know what kind of output you are. I don't know what is the schema. I don't know what is the type, and so on and so forth. So they will say, we will have to rewrite that, into something that we can deploy. Okay? So, I mean, rewriting is always a bad thing, and also, most of the models aren't still available on the JVM. Anyway, but we can say now, yeah, but with Spark, we have PySpark, we have Spark R, we have data frame. And what I say is that, yeah, okay, but they are just late APIs. They are very limited. And in some sense, they're not enterprise ready yet. Why? Because these are layers. They are layers onto the real engine, which is Scala. What does that mean? It means that if you want to be able to access the last cutting edge models implemented in Scala, you have to use Scala, in Spark, you have to use Scala. Why? Because this is where they are strengthening the models, they are strengthening the APIs, they are foolproofing the code and so on and so forth. So only when it's done, they expose this API in Python and R. Okay, so the real engine is Scala, the other are just API, with sometimes, and most of the time, I would say, services or layers connected to them that can break, and for sure it breaks all the time, So you would say, okay, but data frame is a little bit different because then you have this kind of DSL. So it's a DSL that is harmonizing the way you can work with the engine behind. But it's again a DSL, right? So it opens some doors, but it closes a lot of doors. When you do machine learning or optimization, you have to go a little bit deeper. And how to do it in Spark is by creating 2 things. Either you create UDFs, or you use map partitions. I don't know, who knows map partitions? Okay, so map partitions is just a function that we run not only on one item, but on a bunch of items. And this bunch of items is a data partition. Okay, that means that you can do local optimization by using array, for instance, where you can aggregate some computation and then you can pass it to the next steps. So this is an optimization which is regularly done in machine learning. But if you do that in Python and R, then you will suffer two things. First, you will have to get the data from the JVM engine behind. So there is something to do. You have to serialize them. Then you have to read them, transpose them into Python or whatever, and then you have to execute a function that will run onto the JVM on the R environment. So you will suffer you will suffer the performances of these systems. So that means that you are stuck by using what has been defined so far. So you're kind of a monkey, for instance. This is what I say. So if you want to stick with that, then there is a high chance that you won't be able to do exactly what you want to do with the exact performance you want to do. Now, so what is missing on the JVM and Scala specifically in order to have those guys happy? I would say that the first thing is to allow them to be able to interactively work on the data, and this is why we have these notebooks. However, the notebooks need to be, already, they must be enterprise ready, I would say. So you can deploy it on the current infrastructure with no pain, and also they should be able to run the code that has been created in the notebook directly onto the cluster. Otherwise, you will still have this transition between the notebook, which is a simple page with markdown and code, to a real project can run in production. So this is one thing that we need to enable for them. So the other things is the models, of course. So Python and R has a long history, and we have also Julia, which is a latecomer, where there are a lot of models have been implemented. The thing is that now we should be able to implement them pretty easily onto the JVM. Of course, if we have to implement everything, it's going to take quite some time, but we should at first focus at least on the few models that are very interesting for what we need to do, if you want to do business or whatever. So if there may be hundreds of models that are very worth implementing right now, so it shouldn't take too much time to cover that. And actually, Maho did a great job because it reached pretty much this level, but then you have to stick with Hadoop for this one. Right, so, however, what we can do now on the JVM and Scala, and what they are not ready yet on Python and R, for instance, is that we start now creating models directly distributable. They are still working on the local machine when they create models because they want to stick with Python and R, so they don't have this capability to optimize locally, so they're still doing jobs on local systems, so they are inventing systems to create very good sample, or they are optimizing at the very low level, writing Fortran or C++ code. But I mean, this is still local optimization. So what we can do with Scala, with the APIs that we have in mind, and with databases like Cassandra and streaming like Kafka, we can go very, very far than they can go. And the thing is that there are a lot of initiatives that we should follow, and we should come with others. So I would say that I shortlisted a few ones there that I'm used to. There is deep learning for J, which is a very great tool to run deep learning algorithms onto the JVM, but also on Spark, for instance. And tomorrow I will give a talk with SkyMind, which is the company on top of DL4J, how to run NLP using DL4G. OptiML is a very good project at Stanford. It's a machine learning DSL, let's say, in Scala. They have implemented quite a bunch of models already there. I'm working with the University of Paris 13 on different algorithms. GStream, which is a grow neural stream model, mean shift with LSH, self-organized map, and actually those models are able to discover new cluster on streaming data. It's not like k-means. When we think about cluster in supervised, we think about k-means, and then you have to fix k. Actually, here we don't have to fix k anymore. So this hyperparameter can be evolving with the time. Of course, we have MLlib from Spark, and we have other friends on Spark packages that you need to check. The Spark Notebook is there for the interactive sessions. And Figaro, this is one of my favorites. Figaro, I'm a graph guy, and Figaro is the mix of machine learning and graph because it's a probabilistic programming language. And you can do very fancy stuff. I mean, this is worth checking. We're not there yet because the way to optimize this kind of model is still tough. It still takes a lot of computation time. But I mean, this is one area where I would like to work for the coming years. I mean, it's a good mix of graph computing theory and machine learning. And what I've discovered recently is that there are many universities around the world that are starting teaching Scala directly to their data scientists. Why? Because if they think that their students have to have a great job afterwards, not only creating great papers, what is hot now is to create new models on distributed data systems, right? And as I said, creating new models means that you have to write that in Scala. So if they have to understand how the current models have been implemented, they have to look into the Scala code. If they want to create new models, they have to write the code into Scala. I don't mean that they are writing very beautiful Scala code, but at least it's Scala. It can be productized easily. If you want to check the Paris code there, the 3 projects, the code in Scala is not that bad, but it's not so good too. I mean, there are a few things that we see that they are coming from Python and R, but this is our task to help them. I mean, they are very clever. They move very fast as well, so there is no problem with that. So this is exciting moments for us, and this is why this notebook that has been written by Dean has to be reused time to time in order to see to show you should move into the direction.